It's the question that always comes up when thinking about the origin of the universe: what came before the Big Bang? And if there was no before, what was the cause of the Big Bang in the first place? Until a few centuries ago, the answer was easy: some eternal deity set everything in motion. Even Isaac Newton believed that God created the universe some 6,000 years ago. Later, many scientists, including a young Albert Einstein, assumed the universe itself to be eternal and everlasting. Of course, stars could be born and die, planets could collide, civilizations could arise and fall, but on large spatial scales and over long periods of time, it always looked roughly the same as it does now. Only in the 1930s did convincing evidence of the expansion of the universe appear, and in the 1960s, its origin in the Big Bang was confirmed. Such a radical revolution in the scientific worldview has not occurred perhaps since the recognition of the heliocentric system. But then, two equally difficult questions arose. First, what actually was before the Big Bang? What was space like before it began to expand, and how long did it stay in this primordial state? Secondly, everything that has a beginning has an end, so what will it be like at the end of our universe? The English physicist Brian Cox set out to find an answer to these questions, and now, in a world-shattering revelation, physicist and professor of particle physics Brian Cox has just declared that he strongly suspects that the universe existed before the Big Bang, throwing the theory of our origins on its head. We used to think that the universe emerged in that state, very hot and very dense, at the beginning of time, and we used to call that the Big Bang. But now, we strongly suspect that the universe existed before that, and in that sense, it's possible to speak of a time before the Big Bang. Join us as we dig deep into how Brian Cox just debunked the Big Bang. Professor Brian Cox has transformed his field of science in the 21st century into something accessible to everyone, regularly contributing to public debate and discussion. Never one to shy away from the big questions, the physicist previously took on the story of the Big Bang. The idea of the Big Bang first came about back in the 1920s and 1930s. When we looked out at distant galaxies, we discovered something peculiar: the farther away from us they were, the faster they appeared to be receding from us. According to the predictions of Einstein's general relativity, a static universe would be gravitationally unstable. Everything needed to either be moving away from one another or collapsing toward one another if the fabric of space obeyed his laws. The observation of this apparent recession taught us that the universe was expanding. Today, if things are getting farther apart as time goes on, it means they were closer together in the distant past. An expanding universe doesn't just mean that things get farther apart as time goes on, it also means that the light existing in the universe stretches in wavelength as we travel forward in time. Since wavelength determines energy, that means the universe cools as we age, and hence things were hotter in the past. Extrapolate this back far enough and you'll come to a time where everything was so hot that not even neutral atoms could form. If this picture were correct, we should see a leftover glow of radiation today in all directions that had cooled to just a few degrees above absolute zero. The discovery of this cosmic microwave background in 1964 by Arno Penzias and Bob Wilson was a breathtaking confirmation of the Big Bang. It's tempting, therefore, to keep extrapolating backward in time to when the universe was even hotter, denser, and more compact. If you continue to go back, you'll find a time where it was too hot to form atomic nuclei, where the radiation was so hot that any bound protons and neutrons would be blasted apart, a time where matter and antimatter pairs could spontaneously form as the universe is so energetic that pairs of particles and antiparticles can spontaneously be created. A time where individual protons and neutrons break down into a quark-gluon plasma as the temperatures and densities are so high that the universe becomes denser than the inside of an atomic nucleus, and finally, a time where the density and temperature rise to infinite values as all the matter and energy in the universe are contained within a single point, a singularity. This very final point, this singularity that represents where the laws of physics break down, also is understood to represent the origin of space and time. This was the ultimate idea of the Big Bang. Of course, everything except that last point has been confirmed to be true. We've created quark-gluon plasmas in the lab, we've created matter-antimatter pairs, we've done the calculations for which light elements should form and in what abundances during the early stages of the universe, made the measurements, and found that they match with the Big Bang's predictions. Coming forward even farther, we've measured the fluctuations in the cosmic microwave background and seen how gravitationally bound structures like stars and galaxies form and grow. Everywhere we look, we find a tremendous agreement between theory and observation. The Big Bang looks like a winner. Except, that is, in a few regards. 3 specific things you would expect from the Big Bang didn't happen. First off, the horizon problem. If we look in different directions, we see the universe as having the same temperature and density everywhere, but even since the start of the hot Big Bang, these regions never had time to communicate, exchange information, or reach thermal equilibrium with one another. So how did they evolve to reach the same temperature and conditions everywhere? Next, the flatness problem. In an expanding universe, in general, there's a fight between the initial expansion rate that drives things apart and the gravitational effects that work to bring everything back together. In our universe, we observe that these 2 opposing forces are pretty much perfectly balanced, leading to an exactly spatially flat universe. So why was our universe born with those properties? And last, the monopole problem. If the universe reached these arbitrarily high temperatures and energy conditions, then why are there no exotic leftover heavy relics, right-hand neutrinos, magnetic monopoles, and other particles that should be observable and left over today? We can always shrug our shoulders and mutter something like, those must have just been the initial conditions, or, the way the universe was born, but that runs counter to the enterprise of science. Instead, we look for a mechanism that would mandate and set up these conditions. That mechanism sprung forth in 1980 in a remarkable paper by Alan Guth, who noted explicitly that an early, rapid, and relentless phase of exponential expansion where the universe's energy was not distributed among matter and radiation but rather was inherent to the fabric of space itself would solve all 3 of these problems. But because inflation represents an exponential expansion of space, rather than one that terminates in a singularity like the original model for the Big Bang, it sets up a very different picture of the beginning, a whoosh that led to a Big Bang rather than the emergence of time and space from a singular state. Now we get to address the really big questions. What does all of this mean for the true beginning of the universe, if such a thing even existed? Well, the bottom line might be the hot Big Bang definitely happened, but doesn't extend to go all the way back to an arbitrarily hot and dense state. Instead, the very early universe underwent a period of time where all of the energy that would go into the matter and radiation present today was instead bound up in the fabric of space itself. That period, known as cosmic inflation, came to an end and gave rise to the hot Big Bang but never created an arbitrarily hot, dense state nor did it create a singularity. What happened prior to inflation, or whether inflation was eternal to the past, is still an open question, but one thing is for certain, the Big Bang is not the beginning of the universe. But if the Big Bang wasn't the beginning, what was it? What happened before the Big Bang? Short answer, we don't know. Long answer, it could have been a lot of things, each mind-bending in its own way. It's possible that before the Big Bang, the universe was an infinite stretch of ultra-hot dense material, persisting in a steady state until, for some reason, the Big Bang occurred. This extra-dense universe may have been governed by quantum mechanics, the physics of the extremely small scale. The Big Bang then would have represented the moment that classical physics took over as the major driver of the universe's evolution. For Stephen Hawking, this moment was all that mattered. Before the Big Bang, he said, events are unmeasurable and thus undefined. Hawking called this the no-boundary proposal, in which time and space are finite but they don't have any boundaries or starting or ending points, the same way that the planet Earth is finite but has no edge. Or perhaps there was something else before the Big Bang. That's worth pondering. A bold idea of Professor Brian Cox suggested there was a time before the Big Bang, a time in which the universe did not exist at all. He explored this in his documentary series, Universe, where everything begins and ends, stating that before the launch point of the Big Bang, there was no matter at all. All that existed was space-time and an ocean of energy, almost still but gently rippling. This place, as he said, should be imagined as a near-still ocean of energy filling the void. It would have had no structures, and the energy in the space would have caused it to stretch violently, something known in space as inflation. Flipping the Bible creation story on its head, Brian Cox proceeded to explain the science creation story, and the crux of the story is an unimaginably violent expansion which is known as inflation. He said, In the beginning, there was an ocean of energy that drove a rapid expansion of space known as inflation. There were ripples in the ocean. As inflation ended, the ocean of energy was converted into matter by the Big Bang, and the pattern of the ripples was imprinted into our universe as regions of slightly different density in the hydrogen and helium gas that formed shortly after the Big Bang. The denser regions of gas collapsed to form the first stars and the first galaxies, and 9 billion years later, a new star formed in the Milky Way, the Sun. The star was joined by 8 planets, including Earth, and nearly 13.8 billion years after it all began, we emerged, blinking into the light. Notably, Brian Cox is not the only one to make such an argument about the beginning of the universe. Remarkable theoretical physics research has revealed a possible window into the very early universe, showing that it may be just the latest iteration of a bang-bound cycle that has been going on for, well, at least once and possibly forever. According to the study, the physics that we use to understand the early universe, a wonderfully complicated mishmash of general relativity and high-energy particle physics, can take us only so far before breaking down. As we try to push deeper and deeper into the first moments of our cosmos, the math gets harder and harder to solve, all the way to the point where it just quits. The main sign that we have terrain yet to be explored is the presence of a singularity, or a point of infinite density, at the beginning of the Big Bang. Taken at face value, this tells us that at one point, the universe was crammed into an infinitely tiny, infinitely dense point. This is obviously absurd, and what it really tells us is that we need new physics to solve this problem. Our current toolkit just isn't good enough. To save the day, we need some new physics, something that is capable of handling gravity and the other forces combined at ultra-high energies. And that's exactly what string theory claims to be, a model of physics that is capable of handling gravity and the other forces combined at ultra-high energies, which means that string theory claims it can explain the earliest moments of the universe. One of the earliest string theory notions is the ekpyrotic universe, which comes from the Greek word for conflagration or fire. In this scenario, what we know as the Big Bang was sparked by something else happening before it. The Big Bang was not a beginning, but one part of a larger process. Extending the ekpyrotic concept has led to a theory, again motivated by string theory, called cyclic cosmology. Technically, the idea of the universe continually repeating itself is thousands of years old and predates physics, but string theory gave the idea firm mathematical grounding. The cyclic universe goes about exactly as you might imagine, continually bouncing between big bangs and big crunches, potentially for eternity back in time and for eternity into the future. As cool as this sounds, early versions of the cyclic model had difficulty matching observations, which is a major deal when you're trying to do science and not just telling stories around the campfire. The main hurdle was agreeing with our observations of the cosmic microwave background, the fossil light left over from when the universe was only 380,000 years old. While we can't see directly past that wall of light, if you start theoretically tinkering with the physics of the infant cosmos, you affect that afterglow light pattern. And so it seemed that a cyclic universe was a neat, but incorrect idea. But the ekpyrotic torch has been kept lit over the years, and in recent years, many physicists have explored the wrinkles in the mathematics and uncovered some previously missed opportunities. These scientists study the theory of the Big Bounce, suggesting the universe is expanding and contracting, seesawing back and forth in a massively big-picture timeline. Some bouncers believe this happened just once, while others believe a cyclical bouncing is what makes our universe. And while the Big Bounce still requires large leaps that must be explained with generous scientific hand-waving, proponents say it's a lot less than with a model of the Big Bang they say is fatally flawed. The Big Bang, as told, relies on an idea called inflation, the massively, unfathomably fast increase in volume of the universe in the tiniest fractions of a second following the Big Bang. Cosmology is certainly a field that relies on some huge and fantastical ideas, but some cosmologists have criticized inflation for being overly neat, to the point of contrivance. But inflation also could imply the existence of an infinite number of universes. Physicists discovered that inflation goes on forever, stopping only in some regions of space. These bubbles are thus closed off from each other, effectively becoming isolated universes with their own laws of physics. According to this theory, we live in one of these bubbles. That's why the Big Bang falls apart, or at the very least doesn't complete the picture for Big Bounce researchers. After all, What are we missing in a scenario where we have just our bubble? Everywhere else could be different. In our pockets, as an explanation, it's like building IKEA furniture and deciding the hardware you didn't end up using must just be extra. But back to the big bounce, if the theory requires an amount of new or exotic explanatory glue, then why is it better? Well, proponents say the idea of a flexible or even cyclical universe in this way could explain a lot of the bigger missing pieces of the Big Bang without requiring a hand wave toward a multiverse where any physics can be rationalized. And quantum mechanics has just enhanced the big bounce, suggesting ways that a universe bounced down to a mere particle could superposition itself inside and outside of a physical limitation. For example, whatever the case is, when it comes to cosmology, the missing pieces of our understanding mean there should always be room for critiques and new ideas. A related theory holds that the Big Bang wasn't the beginning of everything, but rather that it was a moment of symmetry. In this idea, prior to the Big Bang, there was another universe identical to this one, but with entropy increasing toward the past instead of toward the future. Increasing entropy, or increasing disorder in a system, is essentially the arrow of time. So in this anti-universe, time would run opposite to time in the modern universe, and our universe would be in the past. The idea assumes that the early universe was small, hot, and dense, and so uniform that time looks symmetric going backward and forward. If true, the new theory means that dark matter isn't. Physicists have proposed that our universe might be just one of a twin, a mirror anti-universe, governed by a fundamental symmetry called Kaplan symmetry, charge, parity, and time. This symmetry implies that if you flip the charges of all particles, take the mirror image, and run interactions backward in time, the interactions behave exactly the same. In a paper accepted for publication in the Annals of Physics *, scientists suggest extending this symmetry to the entire universe, proposing that there must be a mirror image cosmos with opposite charges, flipped in the mirror, and running backward in time. This model negates the need for a period of inflation after the Big Bang, implying that the universe naturally filled itself with particles. It also predicts the existence of right-hand neutrinos, which would only interact via gravity and resemble dark matter. If true, future experiments to measure neutrino masses or hunt for gravitational waves could confirm the existence of this mirror universe. However, the origin of the universe remains a profound mystery, pushing the boundaries of our understanding. Even with remarkable scientific discoveries, the problem of the first cause, what initiated everything, lies beyond the reach of scientific methodology. As Einstein wisely remarked, this fact should fill us with humility, reminding us that not all questions need to be answered to be meaningful. That's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. Be sure to also tell us what you think about today's content. Your support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.